Hello, everyone, and welcome to this week's Smart Seminar series. It's my pleasure to introduce Dr. Priya Panda. She's an associate professor in the Department of Electrical and Computer Engineering at the University of Southern California, which she started this position in the beginning of fall 2025. Before joining the University of Southern California, Dr. Panda served as an assistant professor at Yale University from 2019 to 2025. And most recently, she was a visiting faculty researcher at Google DeepMind, where she explored cutting edge topics at the intersection of machine learning and hardware efficiency. Dr. Panda's research lies at the exciting crossroads of algorithm hardware co design for efficient AI ML, neuromorphic computing, and spiking neural networks. Her work pushes the boundaries of how intelligence can be embedded efficiently in hardware, bridging fundamental theory with real world impact. She received her undergraduate and her master's degree from BITS Pilani in 2013 and her PhD from Purdue University in 2019, where her collaborations with Intel Lab contributed to advanced large-scale spiking neural network algorithms for Intel's neuromorphic chip. Dr. Panda's research excellence has been recognized through numerous honors, including the Amazon Research Award in 2019, Google Research Scholar Award in 2022, DARPA Riser Award in 2022, NSF Career Award in 2023, DARPA Young Faculty Award in 2023, and the DARPA Directors Fellowship Award in 2025. She was also named to Purdue's Engineering Inaugural 38 Under 38 list in 2024. Her group's work has earned multiple Best Paper recognition, including the IEEE TCAD Donald O. Pedersen's Best Paper Award in 2025. So, with that brief introduction and this wonderful opportunity, please join me in welcoming Dr. Priyadarshini Panda for a wonderful talk. And we are looking forward to it, Priyadarshini. It's all yours now.
Hey, thanks, Somdata, for having me. Yeah, so since the group is small, I guess I'm going to make it a little bit more informal. So please feel free to stop me during my talk. I have, the slides can run in till the end of the hour, but I'm happy to stop at a point where you want to discuss. Um, and again, I think the group here is also interested in some of the SciML applications. So I have some of the things that we've been doing as a part of our collaboration with Brown University at the end. Having said that, today I thought I'll give you a more introduction to spiking in general, what are its advantages, how do you actually need to deploy it, what kind of efficiency, when we talk about efficiency, what are we looking at in case of a spiking model, such that some of you who are interested in taking this new type of an architecture and new type of an algorithm towards the scientific ML problems, you can possibly make a better decision based on this. Okay, so my group in the past couple of years at Yale and now at USC has been continuing to think about how to design efficient machine intelligence. And we've been looking at both algorithm and hardware based innovations in order to essentially make these strides. And when we think about algorithm and hardware co-design, we're always thinking about how we can take biological inspiration, meaning as I will show you, we take inspiration from the brain, whether it is the way the architecture of the brain is, whether it is the learning principles in the brain of how memories are formed. So we try to abstract them out and try to see what type of algorithms and hardware as a result we can build. So this is sort of like preaching to the choir. We all know today there is a lot of significance and criticality to building energy efficient AI. And the reason is all the devices that we want to embed AI in are essentially limited in terms of resources or power, right? Whether it is a smartwatch or a phone, even self-driving cars, if you want to make them as autonomous as possible, we really cannot anymore have these large models being deployed there because their energy consumption is reaching the pretty large limits. And this curve here essentially explains as to how the model's need for computing has has increased so much that it has far exceeded the way in which our hardware improvements have occurred in the last couple of years. Showing in this curve, it's the pre-GPU era, meaning that, like, prior to 2012, before the AlexNet revolution came in, we see that roughly the model sizes in this era were doubling roughly every 2 years. And this was in tandem with Moore's law, right? But post GPU computing era, we started seeing this rapid growth in AI. And as a result of that, we are living today in a place where, most of our technologies are somehow embedded with some form of intelligence. Having said that, it comes at a cost, meaning the models are becoming more capable, but they're also becoming more and more bigger and larger. So their sizes are doubling roughly at a cost of every 2 to 4 months. And this is far exceeding the timeline in which Moore's law happens. So the compute demands of the DNN are basically much, much larger than the advancements in hardware today. So as a result of that, we really need to think about algorithms or AI models that need to be hardware efficient from scratch. And then the question is, how do we derive that? So in my group, while we look into, like, we have a very broad research vision in our lab. We look into efficient AI techniques in the conventional world. We look into some of the robotics applications, but then there is a very strong wing where we also look into neuromorphic computing. And neuromorphic computing actually offers us a means to do bioplausible co-design, meaning that we develop models which are adhering to some energy budgets or adhering to some power budgets. And just to give you an example, for example, deep neural network, this is a standard CNN doing detection, let's say. A simple recognition of this kind expends about 100 watts of power during inference, and this 100 watt can change depending upon whether you are using one of the legacy GPUs or one of the high-end GPUs today. And then on the other hand, human brain, our brain, we perform impressive feats. I'm talking to you, I'm moving my hand, I'm thinking about what I'm going to say next. All of this is happening dynamically, all within a very meager power budget of 20 to 30 watts. And while we know very little of the brain today, and neuroscience and people in the whole biological brain science community are still thinking about, what makes the brain so intelligent and what are the mechanisms behind it. But as an engineer, over the years, we have figured out that there are certain mechanisms in the brain that probably make it so efficient. The one is in the brain, the communication and computation in the between neurons, or which can be thought of as the compute elements. They happen through these extremely sparse events called spikes, and because of that, we feel that, that's one of the reasons for energy efficiency. And the other reason is that if you think about the brain's architecture, we have our synaptic structure, which is basically can be thought of as the memory, and then we have the neuronal elements, which is can be thought of as the compute. These are all co-located. It's all a mesh, right? Neurons and synapses in the brain. So there is nothing like, today's von Neumann architecture where the neurons or the compute and the memory are separate and there's a bus connecting between them, right? So this co-location memory and compute structure is also what makes the brain massively parallel, right? So we want to take some of these ideas and try to see what type of hardware abstractions we can build and algorithmic abstractions we can build. So with that in mind, for spike-driven aspects, we decided that we want to look into this new generation of neural network, which is called a spiking in neural network. And it essentially harnesses this idea of binary and sparse computations between neurons. And turns out that if you push them into hardware, it turns out you can actually get rid of the multiplier in a standard dot product operation. So when you do spiking neural networks, you, instead of a multiply and an accumulate to do a dot product, you just need to do an accumulate. I'll show you how it occurs actually in a later slide, but this multiplier less computation also gives rise to that hardware efficiency because you're getting rid of it. Then on the other side, which is this co-located part between compute and memory, we decided that we want to think about a emerging technology and emerging architecture there. And one of that became that is currently under study by a lot of device researchers, circuit researchers, and then as a systems person myself, I am thinking about how to take these new innovations and build legible architectures out of it. What I have been looking into is using these non-volatile memory-based analog computing architectures in order to do efficient computations, right? And turns out that if you take this analog computing infrastructure, it turns out that the model becomes way more area efficient, high in terms of performance. Performance is basically throughput in this case, meaning the number of inferences you're doing per second becomes larger. And then it is also a low energy version as compared to a standard CMOS based architecture like that of a GPU or a TPU. So the way I have organized this talk today is that I'm going to give you some basic idea about the kind of algorithms that we have developed in SNNs, at least the ones that have become a workhorse for our group in order to scale to different types of applications. Then I'll also talk a little bit about hardware. Without going into the details of the hardware, I want to tell you, like, when I say energy efficiency, are those numbers really legible? Because, you really need to put this on hardware, and there is no like proper commercially available hardware for spiking today. So we had to build our own simulators, hardware simulators, to do benchmarking, and some of these are very realistic simulators. So I wanted to show you some of those results, and based on those results, we again found out that the algorithms are not as efficient. There are some overheads that we need to mitigate, and then we started coming up with some co-design principles. So I'm going to touch base upon these topics. Having said that, since the group is smaller here, I would like to have more conversation with the group. So wherever you think that you've had enough or you have any questions, please stop me, and I'm happy to go into a conversation. Um, so before I go forward with the algorithms, I want to firstly give you an idea about, like, what is the fundamental difference between a spiking network and that of a standard, like, conventional network. So I'll be calling the conventional network an artificial neural network, or an AN, and both are artificial, but this is just a terminology I will keep throughout my talk. So with a conventional network, we know we process real valued inputs. They go through, let's say in this case, a fully connected architecture, and then you will go through some nonlinear activation and give you some output. In case of a spiking network, these inputs are essentially coming in as spike trains. So wherever you see a line here, it's a 1. Wherever you don't see a line, that means it's a 0, right? So you have these kind of binary spike streams coming in, ones and zeros, right? And they are being processed by the neuron, and then it goes to the next layer essentially. So if you look at the neuronal processing, what happens is that in both the cases, the inputs goes through this weighted summation operation, right? And then it goes through a nonlinearity. In case of a standard ANN, we use ReLU, GELU, SILU, all these new types of activations have come up. Here, in case of SNN, the most popular activation function that is in use today is this leaky integrate and fire activation function. So just to kind of give you an idea of what is the leaky integrate and fire activation function, it turns out that as the neurons are input spikes are coming in, there is this quantity called a membrane potential, which integrates or leaks in the presence or absence of spikes. And as soon as this if membrane potential crosses some user defined threshold, that is the time when we say, okay, the neuron, this output neuron is ready to spike right now. So it goes ahead and spikes, and then we reset the membrane potential, and it continues its job. So going back, so this is basically what I'm showing you here. So there is this kind of a non-linear dynamical quantity that keeps on rising or coming down depending upon how spikes are coming in. And then we always compare the membrane potential value at every time step against a threshold. Now, if you think about it, the spiking neuron dynamics are very continuous, right? But in simulation, we have to discretize it, right? So we actually do a discretized simulation of spiking neural networks. So it is nothing like, even though they are continuous time dynamics, but to implement them, to deploy them on standard GPU PyTorch frameworks, we need to do a discretized solution. So then the question here one can ask is, backpropagation, can we apply backpropagation or gradient descent training towards these models which have this very, very defined non-differentiable activations? Because, there is a thresholding function that you're using in order to generate a spike. So through a thresholding function, you cannot really pass a gradient. So the question is, what type of learning algorithms will be viable that will allow us to train these models? So that question became a crux of research in the early 2015 onwards, like when spiking networks were taking off. So one of the main questions we started asking during that time when I was a PhD student and then continued on as I joined Yale as a faculty is, what type of training mechanisms will make these models work, and not only work, but we scale them up, right? I mean, right from smaller models which were just doing MNIST, we wanted to improve it to ImageNet, let's say. So primarily today, if you think, there are three types of main algorithms that are present and that are being utilized in some form or the other. The first is an STDP, or a spike timing dependent plasticity algorithm. It is a Hebbian learning based rule, and then it is a completely unsupervised rule, and it happens in a local manner. So there's no global supervisory signal. Turns out that it is good, it is biologically plausible, but it cannot be scalable to large networks. And as a result of that, we could only do very simplistic models like MNIST or some simple audio recognition tasks with it. The other thing, then we started thinking about, okay, let's take advantage of an standard ANN itself. So if you have a pre-trained ANN, can we convert to a spiking neural network using some normalization techniques? So that also became very popular. It is still in use today. And turns out that that is good, but then what happens is, when you do this pre-trained conversion, you're really not taking advantage of the dynamics from scratch, right? This temporal dynamics that you have, very unique to a spiking neural network, the sparsity that you have, very unique. The sparsity meaning every neuron is not going to spike at all times, right? That sparsity can be leveraged on hardware. But if you do this conversion, maybe you will get like, you'll not have enough sparsity to take advantage of. And the temporal dynamics are all, anyways, not a part of the training process. So it turns out we got good accuracy, but then we wanted to further improve it. So then the question was, okay, let's now start thinking about some backpropagation gradient descent based schemes with spiking. And there we found out that the training from scratch using, came up with a version of backprop through time using surrogate gradient descent that allowed us to pass some gradients through this non-differentiable function, thresholding function. And that actually started leveraging the time statistics. And turns out that in terms of a trade-off between efficiency, accuracy, even robustness, this sort of an algorithm worked very well. So some of the works that I will be talking to you in the next couple of slides are all going to be based on a version of backprop through time that uses surrogate gradient descent. Okay. The other thing that is also important when you learn about spiking neural networks is the way we encode the inputs. Because real world data, let's say, if you think about images, it's all coming as pixel data, right? So you have to convert this pixel data into spike train. Now, there are different ways of doing conversion. The more popular ones are rate coding and direct coding. Rate coding is basically taking a high pixel intensity, converting into a spike train with more number of spikes. So pixel intensity is directly proportional to the frequency of the spike train. So that's one way of doing it. Direct coding is when you basically say that, okay, what I'm going to do is that I have this learnable embedding layer in some way before we put in some spiking neurons. So during the training process itself, the embedding layer will decide through the training how the spike train is produced. So that also became very popular, and most of our works either uses direct coding or rate coding actually. Temporal coding is actually the most efficient way of coding, because here you will produce only one spike per neuron, meaning it is the most ideal case, right? And here you're embedding the information of the pixel, let's say the value of the pixel, in the timing of the spike. So if it's a high pixel intensity, you will encode it as a early time spike, a low pixel intensity as a later time spike, let's say. But the problem is training with such very sparse data is also problematic. But I'll show you, like, with some of our collaborators at Brown, we were able to do some temporal coding based modeling for wave equation data, and for detecting, for doing wave localization. So that is an application we've just started thinking about. Okay, so with spike-based propagation, again, I just to kind of tell you, like, what are we doing when I'm doing this back propagation through time with surrogate gradient descent? The main thing, and this is a very, very primitive picture of how we do it. But if you see, like, a standard neural network will have a forward pass and then a backward pass. In the backward pass, when you're calculating the loss, with respect to the weights, the derivative of the loss with respect to a weight, there is this function f prime you need to calculate. And this is where the discontinuity comes into the picture because of the thresholding function that LIF has. So all we need to do is approximate this, right? So we can, as soon as we approximate this, we can come up with some kind of a continuous version of that. So that's all we do. And there are ways in which we have approximated. We can do exponential approximation, we can do linear approximation, we can do some kind of a sublinear approximation. So all of these are papers from different groups. And then again, with a lot of heuristics and theory, people have figured out what is the best approximation that people can use. But what I want to tell you is that when we are doing this kind of a backpropagation from scratch using spiking dynamics, firstly, we are using the leaky integrate and fire neuron. That means that the temporal dependency is intact during training. And turns out, as I will show you later, that in a spiking network, you have to process spikes, right? And these spikes are coming in over a period of time that I need to discretize when I do the simulation, right? So that means that, let's say, 100 millisecond spike train, I will have to discretize it into, like, 1 millisecond windows. So I have to process it for 100 time steps, if you can think about it, right? So then, like, you have to process it. So 100 times steps meaning you have to show the input, let's say 100 times, something of that sort, right? So instead of one forward pass, I have to do 100 forward passes. Now that is not good. You want to go to very low latency regimes, because in case of an ANN, you will do one forward pass and one backward pass. So all these temporal aspects is not really going to be useful for you, unless, like, you're working with temporal data to begin with. So the question is, like, how can you lower the latency? How can you encode more information with in a shorter time frame, or time period, right? So when you do the encoding, you take the real world data and encode it into a shorter time period. That's what is important. And turns out, in case of, if you do the training well, then automatically the training figures out that, even though you assigned a larger time period to begin with, but it can get rid of some of the time steps at the end or time steps in the middle, depending upon what it finds useful and what it doesn't find useful. So turns out that's also an advantage of this spike-based backpropagation. But the original spike-based backpropagation as is, it turns out we cannot also scale to very deep architectures. When I say very deep, this was like 18-layered, 20-layered architectures, of the CNN, from the CNN era. So one thing that we devised, and this became a pretty workhorse algorithm technique for us in our group when we started building spiking networks, is that we wanted to take advantage of batch normalization. Batch normalization, as we all know, became a game changer for training deep models. And the idea is that you insert a batch norm layer between, let's say, a conv layer and an activation layer, right? In case of a spiking also, we do the same thing. Now we insert this batch norm layer. It's called a batch norm through time layer. And the temporal aspect comes from the fact that since X is now coming in over time, so it is xt, so the gamma, which basically the batch norm parameter, that is the learnable parameter associated with this batch norm layer, that should also vary over time, right? So that was the main, it's a very simple trick we came up with, and turns out it worked very well. So just to tell you, like, how does the equation look like? So this is a standard LIF equation where the membrane potential looks at the previous value of the membrane potential and the current input current, input spikes coming in. And then what we insert is like the BNTT layer just before the basically this weighted summation output. And the BNTT layer is pretty similar to what you would have done in general batch now, where you have this gamma parameter and you take the input current and subtract it from the mean and divide it by the sigma, right? So the gamma is the learnable parameter here. The only thing to note here is that the gamma is changing over time. So with every input time step or with every input variation, the gamma will also capture that variation. That's all we wanted. So turns out that actually when you insert BNTT as a training parameter, as a trainable layer in our models, when we are training our spiking networks from scratch, the kind of activity we saw is very, very different from prior models that were, let's say, trained using just standard backpropagation or even conversion. So if you see here, I'm plotting the average activity over different time steps, right? So average activity meaning I'm just calculating the total number of spikes divided by the total time period across the entire network, let's say. So you see that for different layers, let's say conv1, conv2, here, there is initially no activity and then it saturates after a certain point. It's the same thing with surrogate backpropagation as well. No activity initially and then it saturates. Every layer has a different spiking rate essentially. But in case of BNTT, there is this kind of a rise and fall. It's like a bell curve, right? So the first layer spikes and then goes down. Then the second layer spikes and then goes down. Third layer spikes and goes down. So we wanted to understand why is this happening, this bell curve. And then when we looked at the values of this gamma that was that we recorded after training. So this is all post training. Once the gamma values were fixed, we looked at the values. It turns out that this gamma has the maximum gamma has a time shift. What do I mean by that? So I'm plotting the gamma across different layers, across different time steps, you see. So that's why that gamma T version comes. So you see for conv layer 1, the gamma T has maximum value at first time step, right? And then for conv layer 2, the gamma T has maximum value at the 5th time step. For conv layer 3 at the 8th time step, and so on and so forth. Meaning that the maximum gamma value shifts to a later time step. And as a result of that, because gamma is what? Gamma is the factor that is associated with how much of input current comes in, right? So if gamma is large, wherever in whatever time step gamma is large, that's where you will have the maximum input current. So in some way, that's why we see that the first layer spikes early and then has a fall in terms of its spiking activity. Then the second layer spikes a little later, right? Has a rise a little later, and then as a fall. So there's this kind of a temporal propagation of spikes as we go deeper, meaning first layers will spike first and then the second layers. And if you see, this is very intuitive, unlike previous models where this thing was not getting captured at all during training, right? And as a result of this very intuitive way of having this temporal spike propagation, we could also see that it translated to better results in terms of accuracy when we started comparing with methods when we started basically using our model for doing image recognition tasks, let's say. So here I'm just showing you that as compared to previous models where when we looked into conversion methods where the accuracy was good, but they were also using a large number of time steps in order to maintain that accuracy. So that's why I'm just calling it long latency, because again, large number of time steps meaning energy will be also very high. So you don't want to go to that regime. Then there is like surrogate gradient techniques that sometimes you were not able to train with a complex data set, but with BNTT we started getting very good accuracy at extremely reasonable latency numbers. So short latency while preserving accuracy, that's what we saw. Now what you want to also see is that ultimately that short latency also translates to actually energy efficiency, right? I mean, you also want to see that the overall network, the spiking activity in the network is in general sparse, because that's what we are taking advantage of when we build an hardware, the whole sparsity, that all neurons will not spike at all times. So there has to be a level of sparsity there. So we found out that as compared to previous methods, we also found that our spike rates were also much lower, right? When we trained our model with BNTT, meaning that with much, much higher sparsity, we're able to achieve better accuracy. It turns out BNTT reduces the spike rate by more than 50x or 10x compared to the previous conversion and surrogate methods. The other thing, and this is something just as a secondary effect we saw, that we also found out that since the model was trained using these temporal statistics well, we found out it was also much resilient against adversarial attacks. Adversarial attacks are the gradient attacks that we create. So turns out that when we measure the adversarial accuracy and as we increase the attack strength, so for a general ANN, meaning it's a non-spiking model, you see as we increase the attack strength, it starts from very good accuracy to begin with, but it starts having a fall in its accuracy because of the adversarial attack. In general, we found that spiking networks, because of their inherent sparse temporal nature, are more resilient to adversarial attacks. So this is a standard green graph here is a standard SNN without any batch norm through time like training principle. And then the red curve is when we added BNTT on top of it, we started seeing that, the resiliency is pretty consistent and against both weak attacks as well as strong attacks. So with BNTT today now, we started using it for a lot of applications because we found that, okay, I mean, with this, I can train models, I can train large models, I can train them faster because I don't need to use that much of latency. So we started developing a lot of different types of models using BNTT. So we started thinking about segmentation tasks. Segmentation is a much more difficult problem because you have to go ahead and essentially classify every pixel in the image. Then we also looked into event data. Event data are those data that are captured using these dynamic vision sensor cameras, and these cameras give you spikes directly. So there is no encoding required. So this is where, it's a very good happy marriage between a spiking network and a devious camera generated inputs. And turns out that even when we applied our models on devious camera generated inputs, we were able to get state of the art performance, and the state of the art we got was more than 30% at that point of time, improvement over whatever was the state of the art at that point of time. And again, we were able to maintain our latency, right? We were able to do all of these recognition with very less number of with few time period, meaning the encoding that meaning that the spiking neural network figured out that you don't really need the entire time window. You always need shorter time window to get to good recognition accuracy. Then the another use case application where spiking networks are being heavily used or at least hold promise are these always on applications. Always on applications are those applications where the AI is continuously running. It's continuously monitoring and giving you some feedback or result. One of those applications can be, let's say, your activity recognition. So when you wear a smartwatch, it's continuously monitoring your data and telling you whether to sit down when you're walking every time, right? And so essentially it takes all this data from these IMU sensors, and then if you have some neural network, it can predict from these IMU sensor data what type of activity you are doing. And we found out that instead of using traditional CNN or a LSTM or some kind of a convolutional LSTM architecture, if we use a spike based architecture, we not only get good accuracy, but we get that same accuracy with very low energy consumption. So the amount of energy consumption we were able to reduce was by nearly 94%. And that was again because of the fact that our models were smaller, our models were extremely sparse, and that's what came to rescue when we thought about these always on applications. And with always on applications, having a low energy component is always useful because you don't want to drain your battery life, all your battery life in doing this. So essentially what I want to say is, we were able to capture a lot of different types of capabilities as soon as we started thinking about scaling up spiking models using the algorithm that I told you. And then nowadays we have a slightly more advanced version of those algorithms now. But essentially we started developing federated learning with these algorithms. We started thinking about privacy preserving distributed learning. We started thinking about an interpretability tool, all of that because now we were able to scale up our spiking models. We also started thinking about very recently that, given transformers have become like, a more widespread a workload today, we started thinking about like, why shouldn't we develop spike based transformer architectures also? What is the problem with it? And is there a way to actually see that spike based transformer architectures are going to be better? And turns out that yes, basically the performance of spiking of spike based transformer architectures actually can give you much better accuracy as compared to a convolution based architecture. So there is a motivation to actually go after spike based architectures. So that's what we wanted to then think about, that with spiking, if you're developing transformer architectures, then what type of technique can we use? The other thing we also found out was that in spiking, when we use spiking in transformers, we get this activation sparsity as a free lunch that in generally in transformers you don't have. So what do I mean by that? So this is a typical transformer encoder architecture I'm showing. It has some QKV layers, then the QK transpose, then you have the softmax QK transpose V, which is the attention operation essentially, then some projection and layer normalization and MLP layers. So what we do in a spiking transformer architecture is that after every linear layer, we attach the LIF, right? So every time you will binarize this Q and the K and the V, basically you will binarize it using the LIF operation, right? So these are, after every LIF, you'll have these binary sparse output, zeros and ones, coming in as a spike train. And turns out that when we measured, like, what is the inherent sparsity overall of these different layers of a ANN transformer and that of a spiking network transformer with LIFs inserted, we found out that almost 80 to 85% of the neurons or activations in those layers are not giving out any spikes at all, right? So spiking transformers are extremely sparse, like 80 to 85% sparsity is not something you can achieve in a standard ANN transformer without using pruning and all these techniques, and here you're getting it as a free lunch. So there's a lot of, if you develop the right type of hardware that can take advantage of this sparsity, it can give you a lot of efficiency benefits. The other thing that we were also motivated by was our back to the fundamentals, right? So again, we don't need to use a multiplier, right? We essentially, because now the query keys and values are all going to be binary in nature, so you really don't need these costly multipliers to do the attention operation. You just need simple mux and accumulate rather than multiply and accumulate. The other thing we also found out was that in case of a standard transformer, we need a softmax operation in order to tell us, like, which which sequence is correlated maximally to which sequence basically. But in case of spiking, again, since you're working with binarized data, this softmax nonlinearity can be replaced with a simple LIF nonlinearity, and it turns out it works very well. So no softmax requirement is again a huge benefit, because softmax is actually a very complex operation today. If you see all these papers that are coming up today in developing new types of GPU kernels for running transformers more efficiently or more faster, let's say flash attention, page attention, they're all trying to target some of these softmax computations in addition to some memory based things. But softmax is also something that they want to target, because softmax is a very sequential operation. You have to do it in a row wise manner. It uses a very costly circuits like exponential units, etc. So getting rid of that is a huge advantage. So with spiking transformer, that's also something you get. um oh, sorry, maybe I may have missed a slide here, but essentially what I'm trying to say is that then we came up with an algorithm to build spiking transformers that take advantage of this no softmax and then this high sparsity. And then those of you who are interested, please read this paper. It's a very recent paper that we published in CVPR. But what I want to just show you here is that the accuracy that we get with our work is much like 2 to 3%, 2 to 3 points higher than what was done in previous work. The other thing also I want to highlight is that we are now able to get the same accuracy with very few parameters as compared to a standard a standard ANN transformer, like say VIT or DEIT or a swing transformer, the number of parameters you're dealing with like is 86 million, whereas when we are coming up with the similar accuracy 76 to 78% with 30 million parameters or 66 million parameters. So again, we were able to come up with this spike transformer attention algorithm where we mix spatial and temporal attention together, that achieves state of the art accuracy with parameter efficiency as well. So far, what I have talked to you about is leveraging time statistics during training optimization can enable different facets of spike-based intelligence, right? But the question is, what about the hardware perspective? Are SNNs truly efficient when implemented on hardware? Now, I know we have like 20 minutes left, so I don't know if you want me to continue or should we pause here, and if you want to go into a discussion here, because the next part is a little bit more hardware focused and I just will give you some results, but I'm happy to kind of stop here and have a question. So I guess Souvik or Somdatta, whatever you want to do.
I think we can continue and we then have the question. I think hardware
Okay.
is not something we listen every day, so we'll be interested in
Okay.
that.
Sounds good. Sounds good. Okay. Yeah, so I'll make it a little more quicker and like more brief. I'm not going to go into the details of the hardware related things, but I just want to tell you, like, if you want to develop any algorithms, you need to think about how do you claim energy efficiency. Okay. So all previous works, when they were claiming energy efficiency, they were calculating energy using this very, very primitive formula, meaning that they were calculating that energy for doing the accumulate operation, basically the flops, right? Time multiplied by the number of time steps you have to process an input, multiplied by the overall density of the model, because not all neurons are going to be spiking. So those neurons who are not spiking, for them you will not account for any flops or energy. So this is what you have. So in some way, if you lower the time steps or increase your sparsity, your energy efficiency will improve. But the question is this a realistic evaluation? Uh, Actually, no, it's not a realistic evaluation, because higher sparsity does not always translate to higher energy efficiency. Firstly, sparsity also comes at a cost. There is a lot of overhead in storing sparse matrices, right? And that the question is that, are you exploiting sparsity at the memory level or only at the processing level? So those are all questions that one needs to ask. Similarly, for in-memory computing architectures, it turns out sparsity can never be exploited, because the way these architectures are, these are weight stationary architectures. These are already laid out. So really having sparse matrices will not really help so much. So we really wanted to think about, okay, then, how do you actually translate spiking models to hardware? For doing that, we wanted to then build some benchmarking platforms that will be useful for us to evaluate if a spiking model is evaluated on hardware. These are the kind of benefits we will get. So we built two in-house tools in our lab. One is a systolic array-based tool called SETA, and the other is a emerging technology in-memory computing-based tool called SpikeSim. So I'm not going to go into the details of SpikeSim, but this was, again, it was an inference benchmarking tool for spiking neural networks on IMC architectures. This is also, it's available on GitHub. So those of you who are interested can take a look at the code and do benchmarking of any spiking model. So you give any spiking model, it will tell you ultimately what is the energy latency area, and what kind of non-idealities are present because of the emerging technology that are out there. So you might have to correct those or compensate for those non-idealities during your training process. But what I want to show you here is when we did an energy comparison between a spiking network implemented architecture and a standard artificial neural network implemented architecture on the same type of a fabric, which is this in-memory computing fabric, what we found out is that compared to, let's say, 4-bit models, ANNs, SNNs actually achieve 10 to 25% lower latency and energy at ISO accuracy. So at ISO accuracy, our latency and energy are slightly lower, right? But it is only 10 to 25% lower, not really like, 10x or 20x lower, right? So that means that, but this comes with a caveat that only when you are lesser than certain number of time steps. Beyond, if you go beyond certain number of time steps, if your latency increases, then actually ANNs are lower in terms of energy than the SNN, because all this sparsity related advantages die away because latency overwhelms you. So the question is, you have to always work in a low time step count regime. So that's one of the first learnings. The other learning is that, like, but with lower time steps, the accuracy also falls down quite steeply, right? So if you increase the number of time steps, meaning that you're giving enough time to the model to recognize that data, so there you will have actually good accuracy. But then if you lower the number of time steps of the spiking model, then the accuracy also takes a hit. So the question is, what can you do to understand the trade-off between accuracy and energy with time step as a control knob? The other thing, I'm going to probably skip this part, but the other thing we also found out was that there's an area overhead to implement the neuronal module itself. And we found out you can do some kind of architecture modification to reduce the overhead. And the architecture modification that we came up with was very simple. It was just reducing the number of channels per layer. And that turns out to be a very good way of reducing the area overhead. But what I want to focus here is on this aspect of reducing the number of time steps, because that has a direct impact on the energy latency total trade-off as well as the accuracy trade-off. So what we decided was, one thing is, like, you can reduce the number of time steps uniformly for all inputs, right? But turns out if you do that, then your accuracy will take a hit. The other thing you can do is, can we dynamically vary the time steps based on input difficulty? So this is an algorithmic change that we did based on the hardware feedback that we got. So let's say, as an example, when you see, like, oranges here, the bottom row of oranges are slightly more difficult because, let's say this can be confused as lemons or something also, right? So in some way, if you think about it, that for easy inputs, you should take less time to recognize. That means smaller number of time steps. For the more difficult inputs, you should take longer time to recognize, and that means larger number of time steps, right? So how do you do this kind of a dynamic time step spiking neural network is the question. We came up with an algorithm where we were able to adjust the number of time steps based on the difficulty of the input samples. And essentially, the way we did that is by using what we called as what we call as a confidence thresholding technique. So we take a pre-trained SNN, and then every time an input comes, we measure what is its confidence on that input, right? And by confidence, you can think of an entropy score. And if the confidence is high enough, then we go ahead and stop the model from processing any more time steps for that input. If the confidence is low, then we will go ahead and process that input for the next time step. So it was a very simple confidence-based thresholding technique. And turns out when we actually implemented this kind of a threshold, entropy-based thresholding, where we were able to dynamically adjust the number of time steps real time during inference, we found out that now this slide here has a lot of data, but let me kind of unpack it one by one. So what I'm showing you here is accuracy versus energy delay product. You want to be ideally in this region, meaning lowest EDP and highest accuracy. This is what is your ideal region. So what you see is that the pink curve here corresponds to a standard SNN, right? Meaning that as you increase the number of time steps for a standard SNN, it will have an improvement in accuracy. We know that. But with a dynamic SNN, automatically, because you're doing this variation in number of time steps, we found out in general, the dynamic SNN gives you much better accuracy at overall 80 to 85% reduction in the energy delay product, right? So that's one thing. Then the pie charts here show what is the fraction of inputs that are inferred correctly at different time steps. And this actually is what told us why our algorithm works so well. Essentially, there is like 90 to 95% of the inputs that can be actually recognized by the first time step or the second time step, shown by the yellow and the orange regions, right? So in real world data sets, there's actually a large portion of inputs that can be quote unquote thought to be easy. At least the model perceives it to be easy. So if you can take advantage of this kind of input variation, you can come up with a very lot of nifty techniques to do improvements in terms of efficiency during inference. So this is what we did in case of dynamic time step, but then we were able to take this idea about input variability and apply it to even standard models. Like we were able to develop transformers with conditional exits and attention reuse and attention skips based on this input difficulty. So the idea was a very nifty idea, and we were able to apply it to different forms. I'm actually going to skip this part here, and maybe like to just kind of give you this idea about, like, the last part where we are doing some SciML tasks in collaboration with our team, with our collaborators at Brown. What we started doing with them is that we wanted to take up a task of wave localization, meaning given a wave diagram, we need to know where did the wave start originating from. So what we wanted to do is, can a spiking neural network solve that problem well? And we wanted to see if we can use not just a standard coded SNN, but we wanted to use a temporally coded SNN because we wanted to be very energy efficient. And as I said, like, with respect to rate coding, temporal coding is going to be extremely efficient because ultimately you're encoding all the information in one spike, right? So it's one spike from one neuron versus multiple spikes from one neuron. So what we found out was that temporal coding models are, however, very difficult to train with deep architectures. And we came up with a way in which residual connections or skip connections can be useful to help you train temporally coded SNNs. So what we decided, like, and again, the bottom part is what is more important. So I'm going to just focus on that. So let's say when an input spike is coming in and you have, let's say, a conv layer, and we wanted to use a skip connection to help us train this temporally coded SNN. We found one thing is that, there will be a time discrepancy between the conv layer and the skip connection branch, meaning that if the input spike occurs around this time here, after the conv layer processing, maybe there is some delay that occurs, right? But the skip connection will still see this kind of an input as is, right? So it will be very difficult to combine the information between these two different distributions, and that will lead to accuracy drop when you're doing temporal coding. And since in temporal coding, it's the timing of the information that carries everything, so these kind of discrepancies can really lead to a lot of convergence problems. So what we decided was that we will insert some kind of time delay, and these time delays are again trainable time delays factors that we brought in our skip connections when we were building our temporally coded deep spiking neural network. And then we found out that with the help of this time delay, we started getting this kind of like nicely interacting spike distributions between the conv layer branch and the skip connection branch. So very quickly going over, like, some results, we conducted our experiments on source localization. And this is for a wave equation. The idea is to predict the approximate source location of the wave. Generally, for source localization, we use a regression problem, but we posed it as a classification problem, meaning that we took the wave picture, we actually divided it into different A grids, and then we started giving this grid to this SNN model, and the SNN model needs to tell me that which grid is where the wave may have originated from. So we found out that, like, as compared to a standard naive SNN implementation without these skip connection blocks, our model started getting very high accuracy. The interesting thing we also got was, the amount of latency we got was also very good. Like, meaning, we did not have to process this input for a longer time step, meaning the latency was also preserved. The other thing we also found that, as we increase our grids, meaning the complexity of the design space increased for more finer localization, we found out that, there again, our accuracy was maintained, and while maintaining the latency or the number of time steps. And just to give you, like, the energy cost when you're doing temporal coding, if we compare our spiking architecture with that of a standard ANN architecture solving the same problem as a classification task, the relative energy cost here is going to be, like, almost 710% better than that of an ANN. So this is where the power of spikes come in, right? And if you're able to use the right type of encoding, the right type of sparsity, you can really take advantage of these models for very high energy efficient implementations. So with that in mind, let me conclude here. So the idea is, today the potential for spiking neural networks lies a lot in computing infrastructures where energy is very, very critical. And as a result of that, whether it is training, whether it is inference, we always want to see SNNs as a potential deployment engine wherever you want to think about energy efficiency. SNNs will do very well across all types of data, but they are a good match for time series data where you don't have to encode information into time separately, right? So that is very important. Temporal domain is very important, right? So when I talk to you about the type of algorithms we were developing, when I talk to you about this hardware inside, that number of time steps is what is something you want to control. So temporal domain is key, and the question still remains, and this is something the community is still trying to figure out, that are we using the temporal statistics in the best way, right? So that is still something people are trying to figure out. And whenever you deal with whether SNNs or any type of architecture, and you're making an energy efficiency point or a energy efficiency argument, you always need to understand that you need to do some hardware evaluation, and if the hardware is not available, you have to do benchmarking on some realistic simulators, because then you can really understand and truly reap the benefits of the type of paradigm you're trying to implement, right? So in case of SNNs, we built our own benchmarking workloads, and that helped us develop new types of even algorithms that allowed us to take advantage of the spiking neural networks efficiency. So my final takeaway for all of you is that ultimately we need to really think about co-design in our inherent principles when we are designing new types of applications, and then this co-exploration and co-design will be necessary for next generation neural computing. So with that, I would like to end and maybe open the floor to some questions if there is still time. And yeah, all our codes, everything is actually available on the GitHub website. So please look it up if you're interested. Thank you.
Thank you, Priyadarshini. This was wonderful and truly insightful. Let's open the floor for questions. If someone wants to begin.
I can begin. I have
Okay.
actually a lot of questions written down, but let me ask only 2 or 3 so that others can also ask. So most of the tasks that you showed was classification, right? I mean, how challenging is it to solve regression? Because when you're taking average, right? I mean, I can
Yeah.
imagine in the decimal place the issue will come if you do not have enough spike times.
Exactly. So, I mean, as I said, like we had to also pose that wave localization problem as a
Mm.
classification task, right?
Mm.
I think with right now we are starting to see some. So the way we now target regression is that spiking neural network is not used end to end. We use spiking network as a pre-processor, and then you might still have some standard conventional units as the post processor where the regression task can follow through, right, with continuous values. So spiking network is somehow we are just fitting it in as a module or a plugin in order in those components where it is very energy intensive. So that's where we see like you can start solving regression tasks, but using end to end, people have shown, but then albeit I would say that there is a little bit of accuracy fall. So for example, in our case, wherever possible, we try to pose it as a classification. And if wherever not possible, then the question was, okay, let's not go ahead and replace the whole branch, but rather a part of the branch. Another thing you could do, and this is something I think we've done some papers with George Karnadakis' group at Brown, is we do conversion. So you take a
Okay.
pre-trained ANN, let's say, for all these equations, Navier-Stokes or, the Bellmans or anything. What we decided was we wanted to take a pre-trained regression model, whether it is PIN or DeepNet or whatever, and then convert it to a spiking version, right? So there, actually, your numbers will remain similar, albeit with
Mm.
some margin of error, but the numbers remain similar. So we started with conversion there, and now we are starting to think about, okay, can we kind of, bootstrap conversion with some kind of like, learning to improve the accuracy
Mm.
further or something. But again, I would say that the first layer and the last layer are non-spiking in all those cases.
Yeah, I
The
mean
middle layer
linear. I can
becomes,
expect. I mean, I can
yeah.
expect a linear layer, right? The last layer, and that will probably
Yeah,
solve it.
exactly.
Yeah.
So the first and the last layers are not spiking and not
Okay.
spiking
Okay.
essentially. Yeah.
But when you convert, actually, you only get energy efficiency in the inference time, right? Training is
Yeah,
still
yeah, yeah.
expensive, so that part is
Yeah,
lost.
yeah, yeah.
Also, you mentioned a lot of
So,
time,
so the
spike time
question,
steps.
exactly. That's a great question again, Souvik. So when we convert, you only get energy efficiency at inference, and the question is then why would you need to do it? Well, See, training is done once, but inference is done multiple times, right? I
Yeah.
mean, once this device is deployed somewhere, you will be mostly
Mm.
inferring, your customer is going to infer it
Mm.
100,000 times probably. So I think that was the argument we gave when we
Mm.
were thinking about, like, taking these problems and building hardware for it, and then, like, pushing it to some customers. So yeah, I mean, that argument still remains, right? Whether it is even with foundation models today, people are thinking about how to reduce the inference energy. So inference is
Yeah.
pretty much like, you have to do it so many number of times, and depending upon the kind of scale you're thinking about,
Mm.
the inference amortization, training amortization occurs as more inferences occur in some way. Yeah.
Yeah. Yeah, agreed, agreed. Yeah, and also repeat. I mean, yeah, it's quite repetitive.
Mhm.
Uh, so the spike sim I found quite interesting that you have developed, but that you said was only for inference, right?
Yeah, for not for training. So I did not
Okay.
talk about SETA. SETA was for training, but that was a
Okay.
CMOS based accelerator.
Okay.
SpikeSim is completely inference. That means if you have a pre-trained SNN, whether
Mm.
it is regression task or classification, you just give your config to SpikeSim and initialize the SpikeSim parameters. Let's say, what is the size of the crossbar you're dealing with, what's the size of the NOC, all of that. And then
Mm.
SpikeSim will take those parameters and basically tell you, okay, if you run it on this in-memory computing substrate, then this is the energy latency area. So it's a pretty realistic, but it's only for inference. We don't do training because
Okay.
with training, again, we have to think about backpropagation
Yeah.
modules and
That's
transposable
right.
matrices. So it's
Yeah.
not as easy. Training is a different ball game. But we
Yeah.
did that with SETA. SETA is our
Okay.
CMOS engine. So if you're
Mm.
interested in with that, you would I would definitely happy to kind of talk
Okay.
offline with you on SETA, but that has transposable matrices, gradients, and all. And with SETA also, we found out that there's so much of memory overhead we get because of these
Mm.
repeated, because you have to fetch the gradients over time. Like, earlier the
Right.
gradient, like in a standard model backprop, G is once, but here the G is over
Yeah.
T. So the
But
question is
yes.
that there's so much of time-based memory overhead. So what can you do? So we came up with some algorithms. I skipped it at the end, but we came up with an algorithm where we were able to share computations over time, meaning layer 1 to layer 5, they will have the same
Mm.
LIF. We will never change its
Okay.
LIF, right? So it's
Okay.
kind of
Okay.
like this sharing of computations over time that allowed us to reduce the memory overhead.
Mm.
So during backprop as well. So those are the kind of
Right.
tricks you can do. Yeah, yeah.
Uh, so a follow-up question is, will it support the, let's say, your spike sim, right? The graded spike that Lohi 2 supports. I mean, that energy can we
No,
compute if
no.
it is?
So no. So spy with Loihi supports different forms of spiking neurons. For
Yeah.
us, we always work with integrate fire and leaky integrate fire.
Okay.
But if you want to change it per se, you can, like, we can change it slightly. But I would say it will be more or less like an LIF or an IF at this point of time. Yeah.
Okay. Because actually we are doing some work on this graded spikes for regression kind of task, and we found that graded
Mm-hmm.
spike actually works slightly better than usual
That's
spike.
true. Yeah, we have also seen that. In fact, some of our applications also, we have seen like graded spikes have worked better because of the fact
Mm.
that it keeps like the memory potential is something that you
Yeah.
don't really reset, so
Yeah.
you
Mm.
always keep some timestamp of the memory potential from the
Mm.
previous or from the
Yeah.
past. Um, but we were like at that point in time we were not supporting it. But maybe I
Okay.
can start asking my students to add that to
Okay.
the types of support
Yeah.
tool also.
Uh, and lastly, a generic question. So I know somewhat about SNNs, but in-memory computing is not something we have worked on, so my knowledge is
Mhm.
quite limited. So how do you see these two paradigms, which target the same thing, reducing energy, but in a very
Yeah.
different way?
So in memory computing today, like, even like if you see like a lot of groups who are just device groups or systems groups who are looking into
Mm.
in memory computing, they are trying to use in memory computing to reduce energy for any workload, whether it is
Yeah.
transformers, whether it is
Mm.
reasoning models or
Yeah.
anything, right?
Mm.
So in some way, in memory computing, you can think of it as an alternative way of thinking about architecture than what von Neumann gives you today.
Mm.
Well, both are von Neumann in some way, but what I'm trying to say with von Neumann is that compute and memory are separate,
Mm.
right? Which is standard CMOS and which is
Mm.
today's architecture. Within memory, the compute and memory are embedded, right? So,
Mm.
and using these kind of new types of technologies, non-volatile memory technologies. Now there is pros and cons there, right? With in-memory also, it's not very easy. The read and write, the peripheral circuits are pretty dominant. So people are still trying to figure out, like, where can in-memory really make sense. While technology companies are investing in in-memory, but they are, yes, yeah, themselves not yet convinced to build an in-memory based hardware accelerator, right? But at this point of time, the work is ongoing in terms of which type of a device can make this a more plausible solution, more compatible solution with CMOS, reduce the overheads. So I feel that definitely there is a lot of scope within memory computing. But yeah, meaning it's both top down and bottom up progress that will drive this research. Meaning, by top down, meaning the algorithms trying to drive what type of how the architecture hierarchy should look like, and the device physics driving how should the how should the integration at the system level look like, right? So it's both of them together that needs to come in order to understand, like, how the progress in this field will be there. But you can think of in-memory as an alternate solution to today's commercial hardware architectures
Yeah.
that we have out there. Yeah, yeah.
Yeah. Okay, I have a few other questions, but I will not ask them now. Maybe I'll write an email later
Yeah.
because yes, the talk was very interesting. So maybe others, the other participants, if they have questions, they can go ahead. Although we are already excellent time, but that's fine, I guess.
We can actually have another question from the audience.
I have a question.
Yeah.
I get the impression that this SNN transformers don't really apply to text, but mostly video and images. Is that correct?
Yeah, yeah. So we have not applied to language. The reason why we could not apply to language was that, or not could not, but we did not apply to language, was that with meaning language models are already very good, right? So we need to first work with pre-trained. Let's say you take a pre-trained llama model, or a pre-trained whatever Quen model, DeepSeek, whatever you want to say, and then you have to convert, because without that pre-trained model, we don't have the data to pre-train a language processor ourselves, right? Whereas video and image are all like up for grabs even today. Like, the whole concept of what is a token for image recognition, or what is it, like, next token generation really solved everything in the language processing world. Meaning, by everything, meaning that it build this foundation model for the language processing world, but there is still a question of what would help us build that foundation model for the image or the vision world. So I think, and again, because of that, the data sets availability, everything, so it made more sense for us to go towards vision. With language, the way people are doing, and I think there are some papers coming up today. We just recently in our group also, we were looking at this paper where people were building spiking LLMs, but they were taking pre-trained Quen models or Llama models and then changing the hierarchy of that. Right. So spikifying that and then doing some downstream uh, kind of fine tuning on it. I guess, if I mean, maybe in the future, if I go ahead and do some spiking large language model, I'll also take that route. Yeah.
Very quickly, can you say how you would encode language tokens in as spikes?
Yeah, so the thing is that the way I would do it is kind of like the direct coding, right? So you let the model itself figure out how, like, using the so you basically insert spiking layers right after the embedding layer, and then during the fine tuning stage, let the model itself figure out. Yeah. We don't do the encoding from the token layer itself. Yeah.
But at the beginning, I got the impression that for images, there is a sort of software-based coding, maybe by intensity and time.
Yeah. So you can do that for images, and then we found out that direct coding actually works better even for images. So today, with even images, we don't really convert them into spikes on our own, but rather have an embedding layer with an embedding layer followed by a spiking layer. Then during training itself, the model figures out after that first spiking layer, like how many spikes to produce, right? So we just let it train and get the information. So even with spiking transformers, when we developed our spike transformer architecture stat, and we did the same thing. So we took all these image tokens, these blocks, right? We fed it through the embedding layer. Then there was a layer of spiking, and that's where the conversion, automatically the conversion happened, right? So like let the network figure out, I think, is the more better way to do it. But if you start inserting your own encoding schemes, you have to always take it with a pinch of salt. That maybe for smaller tasks it might be okay, because you can understand how the data distribution is and the type of coding you can do. But for as the data and the model become larger, I think let the training figure it out rather than you figuring it out yourself. Yeah, yeah.
Very good. Thank you. Thank you.
Mhm.
Thank you so much, Priyadarshini. I think we are pretty much over time, which kind of tells
Sure.
you that this group is pretty interested in your topic. So yeah, once again, thank you, and thank you everyone for tuning in today. We look forward to the next week. Thank you. See you all.
Thank
Thank
you.
you.
Bye.
Thank you for having me. Bye bye.
Right.